Hello! This video is about using standard heats of formation, and to begin with, what the heck is standard heats of formation? So the information in your textbook for this is on page 537 to 544. You can reference that or come see me for help. Let's get started. Oh, that isn't what I wanted. Okay, if you take a look in your textbook, page 975, so if you happen to have your textbook around, I would highly encourage you to look up page 975. Now, I'm assuming that most of you are probably not by your textbook because it's at home and you've rarely looked at it. I get it. 975 is what this page is right here. So this page at the bottom of it, you can see this symbol, which I've kind of written bigger, right here. Let's break down what each part of the symbol means. The triangle part means change. So you can remember that when we do change in temperature, we have the triangle with the T, change in temperature. The H we know is enthalpy. Enthalpy is not exactly the same, but for this class it is the same as heat, which is our Q value. The F, the little f right here is called formation. This is called the standard heats of formation. You can see in your textbook value there. And the little circle-y thing means standard. Now standard is just to talk about like at a set temperature. So this is standard at 25 degrees Celsius and 1 atmosphere. Atmosphere is about pressure. We haven't really covered that yet, but that's what standard is. I'm not going to change the values about what temperature we're at or pressure, but that's what that symbol, circle, means. Now if we look at all these parts and kind of put them together, what this means is if you wanted to form a substance, it would take you a certain amount of heat to do that when you're at these standard temperature and pressure. So in other words, let's go to our example. Silver chloride. If you take a look at its standard heat of formation, it's negative 127. What that means, if you wanted to dig up silver and you wanted to get some chlorine gas, both of those things you can kind of scoop up in nature, and you wanted to put those two together, well, when you did that, in order to form it, it would release 127 kilojoules per mole. So the standard heats of formation is how much does it take to form these substances. I'll give you the definition there. Sorry that I kind of wrote over it. You'll have to kind of look at it. But it's the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements and standard states. In other words, scoop up the things that you need to make it. How much energy will it take to do that? Is it endothermic? Or how much energy will you release if you form it? Because it's exothermic. Something to note, you can pause the video at any time. If you look at a few of them like oxygen, or zinc, or sodium, or hydrogen, all of them have a standard heat of formation of 0. That's because you don't form these, you just find them. Like you go find pure oxygen. Sure, you might have to do a little work to get like pure oxygen instead of just nitrogen or something else mixed in there. And this bottom one to find pure zinc, sure, it's kind of like mixed in with ores and stuff like that. But these are elements that are found on the earth, so you don't have to form them, you just have to kind of find them. So anything that's in its elemental form, like zinc, or aluminum, or oxygen, notice the O2, or hydrogen, notice the H2. If you remember Dr. Hofbrinkel, oh yeah, it's back. You can't just find oxygen. If you just wanted one O, you'd actually have to form that. In real life, O doesn't exist, but O2 does. In order to make just O, you'd have to do some chemical reaction to make that happen. Okay, so that's what the symbol means, and if you look on your list of objectives for the test, you are expected to know what the heck this whole symbol means. We just covered that. Now what we're going to do is actually use it. We're going to use it in this equation. I know it looks very fancy. You might not have seen these math things before, but it's not so bad. What we're going to do is calculate the heat of a reaction. Do you remember when you have like a reaction that goes A plus B makes AB, and then you see this change in H here of like 22 kilojoules or something? What we're going to do is find out, how can we find those 22 kilojoules? Well, you could actually do the lab and like find the number. Yeah, that's totally cool. But you can also use like the textbook to calculate that number. Like what should it be? And compare it to what you did get in the lab. And in order to do that, that's what we're going to use this equation for. So this change in H is this change in H right here for that reaction. And we're going to use these big E things. This is called the summation symbol. We're going to sum up the heat of formation of all the products and subtract from that the sum of the heat of reaction of all the reactants. I would definitely write this equation down, but let me show you how to use it. Okay, here we go. What's the standard heat of reaction? What it's saying is, what's the H that goes right here for this equation? That's what we're trying to solve. And that H happens to be that H. And we're going to use this equation. So the first thing I need to do is look up the heat of formation of each substance. So I go in my textbook and I look up O2. Well, that's an element. It takes 0 kilojoules per mole. And then I look up my CO. Let me go back so you can see this. I look up my CO, carbon monoxide. Here it is, and it takes a negative 110. The units are kilojoules per mole. And the other substance I need is CO2, which is negative 393.5 kilojoules per mole. I'll write it in there for you. Like I said, the textbook might be easier, but carbon monoxide, according to the textbook number, is 110.5 kilojoules per mole, and CO2 is negative 393.5 kilojoules per mole. The units I got from the top of the table. Okay, so now I'm going to use this equation. The change in H of the reaction is equal to the products minus the reactants. So my products happen to be CO2. My CO2 is this guy right here, negative 393.5 kilojoules per mole. Oh, my little girl's working up. Now this is per mole, and I happen to have 2 moles. So I need to multiply this by 2 moles. This is for my CO2. My reactants are going to go right here. My first reactant being oxygen happens to be 0 kilojoules per mole, which means I don't have to worry about that so much. But I'm going to add it to, that's where this summation thing comes through. I'm going to add that with my carbon monoxide. Carbon monoxide is 110.5 kilojoules per mole. My little girl's napping and she's waking up. If you could hear that in the video, I'm not sure. Now I happen to have 2 moles of carbon monoxide, so I have to do 2 moles of that. The moles you can see cancels. So in the end I'm just left with kilojoules. But you can see in the equation what I'm doing is adding up all the products. There's only one in this case. And I'm subtracting from that, adding up all the reactants. I've got them in big parentheses here to make that possible. At this point I just have to bust out my calculator, and I did that for you. I got negative 566. And the units would just be kilojoules. That's my end answer. That's the number that goes right here. 566 kilojoules. It's not per mole or anything, because it's 566 kilojoules per 2 moles of CO2. Or per 2 moles of carbon monoxide. That kind of idea. I can see it's a negative value, which automatically told me it's exothermic. Okay, I hope that makes sense. Because next, I'd like you to try this problem. So you have to write it down. If you don't happen to have your textbook around here, you'll have to back up in the video until you can see the textbook slide for these. I'd like you to find the heat of the reaction for this one, just like I did on the last slide. Put that in your Google form and bring your questions to me tomorrow. I will see you then.